Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back once again. So we have been discussing about properties of MMCs. And with regard to the property of any composite, we have seen that it can be obtained from the rule of mixture by the weighted average of the properties of the individual constituents. So for example, if you talk about a fiber reinforced composite, the elastic modulus of the composite EC can be obtained as this, where FF is the volume fraction of the fibers. Okay. And we have also defined the minimum and the critical fiber content for any benefit, any strengthening benefit to occur in the composite material. So although the rule of mixtures generally gives you a higher value for the property, for the particular property that you are looking at, but nevertheless, this gives you a first-hand approximation of the property of any composite material. Okay. So now, if you talk about the strength, that can also be approximated by the rule of mixture. And in a composite material, we always look for a higher strength. So from that perspective, you can say that the MMC technology is also a strengthening mechanism for metallic materials, including aluminium and its alloys. So in this class, we are going to look at the strengthening mechanisms which operate in a metal matrix composite. Okay. So if you remember, I said that the interfacial bond between the reinforcement and the matrix is very important. This is due to the fact that when the composite is loaded, the load is transferred to the stronger fibers through the interface. Because when the load is transferred to the fibers, since the fibers are stronger, they will carry the load, and as a result of that, the strength of the material as a whole will increase. Okay. And that is why if the bonding is not good, then this load transfer will not happen effectively and you would not get the strengthening benefit, right? So this is the load transfer mechanism, which is also known by this name, shear lag model or shear lag theory. So if you look at the load distribution in the fiber when the composite is loaded in a particular direction, it would be something like this when the loading direction is along the fibers. Okay. So it will be subjected to a normal stress which will vary like this along the length of the fiber. Sigma is the normal stress, and it will also experience a shear stress. So the shear lag theory says that the load is transferred to the fiber via the interface, and therefore along this interface you have a shear stress. So let us call that as tau naught. Okay. So what we are talking about here is that you have a composite material like this where fibers are aligned in a particular direction and the loading direction is parallel to the fibers. So let us select a particular fiber element from here and see how the load is distributed. And let L be the length of the fiber. So as I said before, the fiber will be subjected to a normal stress, and as the load is transferred to the fibers through the interface, there will be a shear stress developed along the interface. Okay. So if we neglect the strain hardening, then the shear stress on the fiber surface will not exceed the yield stress tau naught. Okay. So if you take an equilibrium of forces between the stress in the fiber and the shear stress acting on a length L by 2, then this is what you will get. And we are considering half length of the fiber because it is loaded from both the sides. Sigma F is the stress acting on the fibers, and the area on which it is acting is basically the cross-sectional area. So if D is the diameter of the fiber, this is the area on which it is acting, and it will be balanced by the shear stress which is acting on the surface of the fiber. So this is the area on which it is acting when you consider half the length of the fiber. So we can write sigma F as this, right? So here you can see the stress acting on the fiber not only depends on the applied stress, but it also depends on the L by D ratio, okay, which was not there previously when we talked about the rule of mixtures, right? Rule of mixtures talks about only the weighted average, and it does not really care what kind of morphology or geometry you have for the reinforcement, right? But here you can see now the L by D ratio has come into picture. So the geometry or the dimensions of the reinforcement will also play a role on the deformation of the composite material. Okay. And from here we can also define something called a critical length LC, which will be again coming out from this particular equation. So when the fiber length exceeds the critical length LC, it is possible to load the fiber beyond their breaking point and fracture them. Okay. But the fact is, when the load is high, the matrix material also will start to yield. So at a higher load, chances are the matrix will start to deform plastically. And even when the fiber length exceeds the critical length, the average stress at the mid length of the fiber will be lower than the maximum fiber stress. Okay, because as I said, when the load is high, chances are the matrix yielding will also occur. So from that, we can write the average stress acting on the fiber, that is sigma F bar, as as this, okay, where beta is a load transfer function. And now if you come back to this equation with regard to the composite strength that we derived before, now considering the load transfer and also the fact that it also depends on the L by D ratio or the aspect ratio of the fiber, we can rewrite this equation as this one, right? We simply replace sigma fu with this, the average stress on the fibers, which takes into account the L by D ratio also, okay? So from here, you can see that the discontinuous fibers with a smaller length will always produce less strengthening than continuous fibers, okay? Because here it is there in the denominator, right? The L by D. LC contains the D factor, as you could see from here, right? Sigma F by tau 0 is nothing but a dimensionless parameter, a dimensionless number. So L by LC basically represents L by D, right? So when L is small, you can see the strength of the composite will be lower. So you can say that discontinuous fibers will generate lower strength because they have smaller length. So the strength will be lower compared to continuous fiber reinforced composites. So now it can explain the actual observations, what do you practically see, which was not possible to explain by the rule of mixture model, right? So practically you would see if you vary the fiber geometry, the strength will also vary, right? And that is how this shear leg model takes into account the geometry or the dimensions of the reinforcement into account, okay? So it tells you that as you change the dimensions, the strength will also differ, okay? And that is what we practically see. So this model is able to explain the actual observations that we see in reality. Now let us also talk about the dislocation mechanisms of strengthening in a metal matrix composite. So we have seen before, any strengthening comes down to the fact that the dislocation motion is hindered, okay? But that hindrance to the dislocation motion will be generated by different ways depending on what kind of mechanism is actually operating. Okay. So in case of MMCs, there will be a particular mechanism through which that can happen, and that is what we are going to talk about right now. So when you have this kind of solid impenetrable particles, as the reinforcement, then obviously this is going to act as the hindrance to the motion of dislocations, and we can in fact invoke the over-one strengthening mechanism here. The over-one mechanism talks about the bending of dislocations around this kind of impenetrable solid particles when they are dispersed in a matrix phase. And here the strengthening is given by this particular equation, where G is the shear modulus, B is the Burgers vector of the dislocation, and lambda is the spacing between the particles or the interparticle spacing. So from here you can see as the distance between the particles decreases, the strength will increase. And this is what happens when you change the particle size. When the particle size is finer, the distance between them will decrease, and as a result, a composite which is reinforced with finer particles will give rise to higher strength compared to a composite which is reinforced by coarser particles. So this is one of the mechanisms, one of the dislocation mechanisms which can operate in a metal matrix composite, but there could be others also. So let us see the other dislocation mechanisms also. A composite can also give rise to grain size strengthening. Because the presence of the particles will refine the grain size, since the particles will act as heterogeneous nucleation sites. Leading to a higher nucleation rate and thereby grain refinement. So here we can use the Hall-Page relationship with regard to the increase in the strength. And in fact, this can happen during solid state processing also. when recrystallization can occur, and particles above a given size, above a given critical size, can actually stimulate the nucleation during the recrystallization process, the nucleation of the strain-free grains. So that particle stimulated nucleation, or PSN in short, can give rise to a finer grain size. The resultant grain size D can be approximated by this particular expression, where dP is the particle size and F is the volume fraction of particles. Right, so this can even happen during solid state processing also. So let me summarize. In this lecture, we talked about the strengthening mechanisms in a metal matrix composite. First, we talked about this shear lag theory, which deals with the load transfer which happens from the matrix to the stronger fibers through the interface, and that is why the interfacial bonding is so important with regard to the strengthening effect in a metal matrix composite. So this theory basically says that when the composite is loaded, the load will be transferred to the stronger fibers, and from this the average stress on a fiber has been also derived, and we have seen that the average stress on the fiber, that is this sigma F bar, depends on the L by D ratio, or the aspect ratio of the fibers. Okay, so from that we could also derive the strength of the composite by using this particular equation, and here if we substitute this first term with the average stress on the fibers, then the composite strength will be given by this particular equation over here, which takes into account the L by D ratio as well. Okay, so this tells us that the strength of a composite does not really depend on the volume fraction of the fibers alone, but it also depends on the geometry of the fibers, which is given by the L by D ratio, or the aspect ratio. Then we talked about certain dislocation mechanisms with regard to the strengthening in metal matrix composites. First, we talked about the R1 strengthening, and this mechanism basically talks about the bending of dislocations around impenetrable solid particles, and as they do, dislocation loops will be left behind around the particles, and hence the motion of further dislocations will be hindered. Okay, and the strengthening effect is given by this particular equation according to the R1 strengthening mechanism. Here lambda is the interparticle spacing, so it also says that as the spacing between the particles decreases, the strength will increase. Then we talked about the grain size strengthening, which comes into play in metal matrix composites also. This is due to the fact that the particles act as nucleation site, and that will increase the nucleation rate and give rise to grain refinement. And this can even happen in solid state processing when recrystallization occurs. So particles of a given size can stimulate the nucleation in the recrystallization process, and this particular phenomenon is known as particle stimulated nucleation, and therefore in the recrystallized material the grains will be finer, and therefore the strengthening effect will come from the grain refinement strengthening as per the Hall-Page relationship. And with that we come to the end of this lecture, but there is more to come. Keep watching.